Today, in section 7.5, we will consider certain applications of the similarity results that have been proven in previous chapters. These will seem heterogeneous, and that's really the intent. This is a collection of problems and proofs that can be solved with the tools that we developed, and this is simply the place where I've collected them all together. So, applications. The first concept I wish to discuss is the concept of self-similarity. We will find that this is crucial for us in the next chapter. It will ultimately form the foundation of the proof of the Pythagorean theorem, and actually, in some of the work that we're about to do, we will hint at that proof. All right, now what is self-similarity? I have a very simple definition for you, and it's this. When a part of a figure is similar to the whole. A self-similar figure then is, as it were, made up of smaller copies of itself, at least one. So it's an extraordinary idea, first of all, the idea that a part of something should be like an exact copy of that thing, but at a smaller scale. And it will turn out actually that it is possible, in the case of a right triangle and certain other figures as well, to completely create an object out of smaller copies of itself. So let's see some examples of this. So here's, in this diagram, a triangle ABC with a segment BD added so that the angle created, that is angle CBD, is equal to the angle A. Now, what I say in this case is that we have an instance, an example of self-similarity. That is, we have a part of ABC that is similar to ABC. Now, how would we actually establish that that is the case? Well, notice that triangle ABC and triangle BCD share angle C in common. Angle C is part of both. So I will mark that. So now we see that two angles of ABC are equal to two angles of BCD. And of course, then by angle-angle similarity, I will not turn this into a proof, but let me make this observation for you. By angle-angle similarity, it follows that those two triangles are similar to one another. So let us then write a similarity statement. Excuse me. And in this case, we have to take special care. In some cases, it's really quite easy to get the order of letters correct in a similarity statement, but in this case, it is not so easy. Okay, so first of all, let's look at triangle ABC. And I tell you what, I'll call it just exactly that, because we can always choose the order of letters in whichever way we choose for the first polygon, the first triangle in this case. But once we have chosen an order of letters for the first, we must then be careful about the order of letters in the second. So notice what happened when we went from A to B to C in triangle ABC. We went from the angle with the single hash, and we ended with the angle with the double hash. So we must do the same in the triangle with vertices B and D and C. So we must start at the angle with the single hash, which occurs at B, and then we must end at the triangle with the double hash, which is C, which means that the middle letter must be D. So that is our similarity statement. Okay, now what we can do in this instance is we can use this to find the length of AC. Okay, so here it is, AC. We wish to find the length of that, and that's obviously a side of triangle ABC. Now, before we actually do this, which will be straightforward, notice initially that this seems quite extraordinary, right? In previous problems where we had similar polygons, we would need 3 side lengths before we could get a 4th side length, because of course we would set up a proportion, and a proportion contains 4 total quantities. So it would seem, of course, that we need 3 of those. We do, really. To find the 4th, we can only have a variable in one position in such a proportion. But in this case, we only have 2 quantities given, so it will seem mysterious, deeply strange, that we could actually find a side length given only 2. But let's actually write a proportion down. Okay, so let's see. We're given the length of BC, let me mark that, and we're given the length of DC, that is 9. Okay, so that means that we do know a side length in triangle ABC, that is the BC. Okay, so let me begin to write a proportion. Okay, so 12 is the BC from triangle ABC. And to what does that correspond in triangle BDC? Well, B and C are second and third position, so that corresponds to DC, second and third position in triangle BDC, and DC is equal to 9. Okay, so let's now go back to triangle ABC, and well, let's see. we wish to find the length of AC, so I will add that into the proportion, that is our variable. And then let us ask ourselves, to what does AC correspond in triangle BDC? Well, AC is first third in triangle ABC, so that corresponds to BC in triangle BDC, which once again is 12. Oh, and now the mystery is solved. How is it that we can actually set up a solvable proportion with only two quantities? Well, what happened is this, and I will draw arrows to emphasize the point. One of those quantities occurred twice. And why did one of those quantities get to occur twice? Well, that quantity was part of both triangles. And then since the triangle ABC is similar to a part of itself, it should really now come as no surprise that that quantity gets to appear twice in the proportion. Okay, and then if you were to cross multiply, you would have 9 times AC is equal to 12 times 12. And I think I'll pause right there. You can certainly solve this out yourself, but that's how this works. All right, so let's move on to another example. And this one is somewhat more complex, and it will take us just a moment to analyze it. So consider the diagram below. And let me talk you through the stages of this diagram. The way that I think of it is this. We start with right triangle ABC with its right angle at B, and then we add in the segment from B, vertex B, to AC, perpendicular to AC, and that intersects at point D. So this kind of a segment is called an altitude. Okay, an altitude in a triangle is a segment that goes from a vertex perpendicular to the line through the opposite side, and that's definitely what we've done. We've gone from B to perpendicular to the line through the opposite side, that is line AC. And of course that means that we make a right angle when we arrive at AC. And now, consider what has happened when we added in that altitude to AC, which of course is the hypotenuse. Well, we now have three triangles, do we not? We have the original triangle ABC, and now we have the component triangle ADB, and we have the component triangle CDB. So we have three triangles total. And what I say to you is that each of these three is similar to the other two. And how will we prove that that is the case? Well, let me label some angles, okay? 1 and 2 and 3 and 4. And consider the relationships between these. Okay, consider the relationships between these. Well, obviously 2 and 3 are a complementary pair, right? Because they sum up to 90 degrees. But also 1 and 2 are a complementary pair because consider their position within triangle ADB. They are the acute angles. Of course, the angle at D in triangle ADB has to be the right angle, so they are the acute angles in a right triangle, which means that they are complementary. So what we know is this, is that 3 is supplementary to 2, complementary to 2, and 1 is also complementary to 2. So then we have two angles, namely 1 and 3, each complementary to the same third angle, namely 2. And we know from way back in chapter 2 that if you have two angles each complementary to the same third angle, those two angles are equal. That was called the same complements theorem. So we know that angle 1 is equal to angle 3, both complementary to 2. And in the same way, I won't go through the details, but in precisely the same way, we could prove that angle 2 is equal to angle 4. Okay? And as for the similarity of all three of the triangles present, well, consider this. Each of the three has a right angle. Each of the three has an angle with a single hash. You can check, all three of them do. And each of them has an angle with a double hash. That means that the angles of any one are equal to the angles of both of the others, which means that all three are similar by angle-angle similarity. Okay, and we can write a similarity, an extended similarity statement if we like. So we could say, for instance, that triangle ABC, and notice what we did when we went from A to B to C. We went from single hash to right angle to double hash angle in ABC. So let us do the same in the other two. So in the triangle with vertices A and D and B, if we go in that order, that is if we go A and then D and then B, we went from single hash angle to right angle to double hash. So that's similar to A, D, B. And then in the final triangle, the one with vertices C and B and D, well, once again, we need to go from single hash to right angle to double hash, and that would be B, D, C. And this is extraordinary, isn't it? This means that we can take a right triangle, and then when we drop in the altitude to the hypotenuse, we have actually broken up the original right triangle into two right triangles, each of which are similar to the original. That is, every right triangle can be made from smaller copies of itself. It's extraordinary. It's extraordinary. And this will be the idea behind the Pythagorean theorem. Now let us do a problem, which is a little bit algebraically complex, but I wanted to see this. This will lead us quite naturally in the next chapter into the proof of the Pythagorean theorem. So we have the same setup as before. We have the right triangle ABC with the altitude to the hypotenuse BD, which of course makes their two right angles by that old theorem, the perpendicular lines theorem. And we know that AB is equal to 3, and we know that BC is equal to 4, and we wish to find the length of AC. Hint. In the right triangle ABC, we're given the lengths of the two shorter sides, that is the legs, and we wish to find the length of the hypotenuse. Now, of course, if we had the Pythagorean theorem, we could apply it immediately, but we don't, so we won't. So how will we do this? Well, let us label AD as an X, and let us label CD as a Y, and then what we will do is we will now set up some proportions. Okay. Now, remember the locations of the equal acute angles. I will mark those in. And we will use the locations of those angles to set up proportions. Okay, and we'll actually set up two. Okay, so we will set up two proportions, and then we will do a little bit of algebraic work with them. Somewhat more complex than the work that we've seen before, but still not bad. Okay, so let me choose a side first of all from triangle ABC. Let me choose the side that is x plus y. Of course, that's simply AC, but here I'll call it x plus y. And notice that in triangle ABC, that's the side opposite the right angle. Now, let me go to triangle ADB. So for the bottom of this ratio, then, I must choose the side opposite the right angle in triangle ADB, which is 3. Okay, so let me go now back to triangle ABC for the top of my second ratio. Oh, and I do know another side of triangle ABC, that's the 4. And notice that in triangle ABC, that's the side opposite the single hash angle. So what we must now do, oh, no, I think I'm about to change my mind on this. It's entirely possible to set up these proportions in such a way that ultimately you will not be able to solve them out. So let me make another choice. And this is a problem that you often have when you do this kind of work. Okay, let me make another choice. Okay, so I could have chosen the 4 from triangle ABC, but instead let me choose the 3. That's also a side from triangle ABC, so I will choose the 3. And since the x plus y on top was a side of ABC, the 3 must be on top in my second ratio. Okay, so notice what 3 was in triangle ABC. In ABC, it's the side opposite the double hash angle. So back in triangle ADB, I must choose the side opposite the double hash angle, which is the x. Okay, so let me go and do something like this again. Okay, so once again, I'll choose x plus y from triangle ABC, but now let me go to triangle CDB. That is the component right triangle that's on the top. Okay, so x plus y was the hypotenuse, that is the side opposite the right angle, in triangle ABC. So I must choose the hypotenuse in triangle CDB, which is the 4. And then let me now go back to triangle ABC and choose another one of its sides. I will choose the side of 4. And notice that the 4 occurs twice, just like the 3 occurs twice. And why? Because it's a side length in more than one triangle. That's why that can happen. And then notice what the 4 is in triangle ABC. It is the side opposite the single hash angle. So in triangle CDB, we must choose the side opposite the single hash angle, which is the y. Okay, so we've got two proportions. Let's cross multiply both. That is, form product of means, product of extremes, and set them equal. So for the first, I have x times x plus y is equal to 3 times 3, which is 9. And then in the second, I have y times x plus y is equal to 4 times 4, which is 16. So let me do the distribution in each. And the first, I get x squared plus xy is equal to 9. And then in the second, I get y squared plus xy is equal to 16. Now, you might well wonder, well, what do we do with these? How do we solve them out? Well, let me show you a really quite clever move. I will use the addition property of equality, okay? We know that if we have two equations, if we add the lefts of those two and we add the rights of those two, then those two sums are of course equal, because when you add equals to equals, you get equals. So what that means is this, is that if I have x squared plus xy plus y squared plus xy, that's the sum of the lefts, that must equal 9 plus 16, the sum of the rights. Okay, so let me do just a little bit of simplification work. So on the left-hand side, I have an x squared, I have an xy and another xy. So that's 2xy plus y squared is equal to 25. Now, at this point, I'll have to ask you to dig deep into your knowledge of Algebra 1 and ask yourself how you can factor the left-hand side. And it's absolutely factorable. And the way that it factors is this, is it is x plus y quantity squared is equal to 25. And if there's any doubt about that, we can square x plus y off to the right just to verify that indeed they are equal. X plus y squared is x times y plus x plus y. And we talked before about how actually you would do the multiplication. Here, you multiply each term in the first by every term in the second. So you have an x times x, which is x squared. And then you have an x times a y, which is an xy. And then now let us move to the y in the first set of parentheses. We multiply it by the x. So we have another xy. And then we have the y times the y, which is y squared. And sure enough, that's x squared plus 2xy plus y squared. So our factorization back in the original algebra is correct. So we have x plus y quantity squared is equal to 25. And then it will come as no surprise that this means that x plus y is equal to 25. You've done problems like this before. Simply take the square root of both sides. But now look back at the original diagram. X plus y. Those are the two parts of the segment AC. So what we've really concluded is that AC is equal to, oops, let me go back and make the appropriate change. I should have taken the square root of both sides. So I should have taken the square root of 25, which will result in 5. And that means that AC, since it is the sum of x and y, is 5. So there we go. We solved this particular problem out by the use of self-similarity. And hint, hint, this kind of procedure is exactly what we'll use later on to prove the Pythagorean theorem. All right, so let me discuss two final theorems. I won't take the time to actually prove them with you, though I may say a little bit about the proofs. These are two actually very nice consequences, very nice theorems that follow from the work that we have done in this chapter. Okay. First of all, we will have the triangle median theorem, and then second, we will have the angle bisector theorem. And as I said, I'll let you search for proofs, but I will take a moment to talk about these. First of all, the triangle median theorem. First of all, let me define triangle median. A median in a triangle is a segment that goes from a vertex to the midpoint of the opposite side, like in the diagram that you see below. So we have triangle ABC. D is the midpoint of AB. E is the midpoint of BC. The segment AE then goes from a vertex to the midpoint of the opposite side, as does CD. So those by definition are medians. And then we have marked their point of intersection F. And what you will prove is that AF is 2/3 of AE. That is, the part of the median AF is 2/3 of the whole. And this would also be true of the other median as well. That is, CF would be 2/3 of CD. And as for how this will be proven, well, let me go ahead and make a suggestion to you. It begins with, one way to do this, begins with the construction of the segment DE. And then do you notice that a certain familiar theorem, a theorem that we've talked much about, is applicable now? Look at triangle ABC and consider segment DE. DE is a mid-segment. That is, it goes from midpoint to midpoint. And then what follows from that? Well, at this point, we apply the triangle mid-segment theorem. It'll follow that DE is parallel to AC. And then I'll say one final word about this. You should be able to prove then that triangle DFE is similar to triangle CFA. And you should be able to do that by angle-angle similarity. And then I will let you, first of all, worry about the details of how we reach that conclusion, and then ask yourself how it is that you could reach the conclusion that AF is 2/3 of AE from this prior conclusion that triangle DFE is similar to triangle CFA. All right, and then finally the angle bisector theorem, which is one of those theorems when you prove it involves a set of constructions that initially are far from obvious, but what they do are really quite extraordinary. So what the theorem, all I'll do with you now is just simply review what the theorem says, and then with a little bit of help, I think you'll get it done on the worksheet. Okay, so it concerns a situation where you have a triangle, in this case triangle ABC, into which has been constructed an angle bisector. Okay, so in my diagram, BM bisects angle ABC. And then what the theorem says is this, is that the ratio of the pieces of the side that is split by the angle bisector, that is AC, equals the ratio of the two sides of the angle that was bisected. Okay, so what it really says is this, is that the ratio, and this is going to be written just a bit differently than what you see, but it's ultimately the same, that is the ratio of the pieces of the side that are split, of the side that is split into pieces by the angle bisector is equal to the ratio of the two sides of the angle that's bisected. So in this case, AM over CM is equal to AB over BC. Okay, and I have that written a bit differently up above, but ultimately those are the same. So that's what it is that you're supposed to prove. And I will give you the constructions. So I actually give you what is most difficult about this proof.